Hello and welcome to the week 12 of the Sobolev space and partial differential equation TA class. And this is our last week. And in this week, we use this semigroup theory to solve the differential equations. And some in the lectures, you saw some examples of some famous examples of heat equation, wave equation, and the Schrodinger equation. So continuing this, we will see some questions based on this semigroup theory. And first, we will start with a motivating example that helps us to understand that how this semigroup theory is quite natural to help quite natural in solving this in PDs. And then we will see some more problems on the unbounded operators. So let us start our today's session. So the first problem is not a problem, it's just more motivating examples. So, so we have this net omega be a subset of Rn, be open and bounded. This is basically the domain. And consider the following uh, problem based on heat equation. It is a heat equation and U is 0 on the boundary and U at 0 considering to be G. So basically at time equal to 0, I have G. This is my initial state where G belongs to H2 omega intersection H1 omega. So the problem is with the help of solution, with the first solution, construct one CNOT semigroup solution. So here I'm using some basic prior knowledge that with the help of this type of problem, like one can solve with the help of the knowledge of this whatever system liability problem. Like basically we consider the eigenvalue eigenpair problem, and with the help of that we can able to write the general solution. So assuming that the thing to be there. So like it's like we are assuming something here, but it's not a big assumption. One can prove, but the our main aim is to see the motivating C naught semigroup theory, how the that is motivated. So one can have the unique so let's name this problem to be star. Unique solution of stars is given by uxt equal to summation k1 to infinity ak T minus lambda k T phi k x, where lambda k and phi k are the eigenvalue eigenfunction pairs of minus Laplacian on H01 omega. Moreover, assuming phi k to be orthonormal in L2 omega, and this also and we have ak to be nothing but the inner product of phi k with g. G is our function, boundary function for initial state. So it is at L2 Rn. So this can be done. So with the help of this, how we define a one parameter family of operators? So it's like the coming out naturally. So this naturally defines a one parameter family of operators. They are given by Tt from L2 Rn to L2 Rn, and it is given as Tt gx to be summation k from 1 to infinity ak t minus lambda k t by kx. So this is this, and this family actually is defined for all t greater than or equal to 0, because the solution is there. Such that for each g in H2 omega intersection H0 1 omega, the solution to star is given by ut equal to ttg. Moreover, what do we have? We have, if we just consider so first we have, if we just consider one thing, if we consider t0 at g, this will be nothing nothing. But so how this is depending on g, will have this orthogonal expansion. So this ak is actually where our g is playing the role. So this is actually nothing but summation k1 to infinity ak by kx. But this is if we put the value of AK here, so this is nothing but AK is we have defined, as I mentioned earlier, this is nothing but then a product of 5K G, and this is the L2 product, and these are orthonormal basis. So actually this is nothing but and this is nothing but the orthogonal expansion of G only. So this is nothing but G only. So T, so this implies this for all G in L2 omega, we have uh, TO G is nothing but G only. Also, for a fixed G in L2 omega and S and T to be greater than equal to 0, we have TT, TS, if I consider GX. So again, you can see this is actually a, if we take TS, GX, it will be again operator in L2 only. So this TS, GX will be L2 function, then we can apply TT again on it. So we have TT summation K from 1 to infinity, AK, E minus lambda K, S. So this is lambda K, and then we have phi K, X. And now if I apply the uh, definition of TT, so this will be summation J1 to infinity and then we have to take the inner product uh, of this function summation K1 to infinity AK E minus lambda Ks by K, and I have to take the inner product with another orthonormal basis with the indexing J. So this is phi J, and this inner product is in L2 Rn and into E minus lambda Jt phi J X. And finally, so this now we can use this orthogonality relation. So this actually this all the terms will vanish except when k is equal to j. Here all the terms will vanish except when my k is equal to j. So this will actually ultimately I can write this as aj e minus lambda j, and then we have s. And we have this inner product with 5k and 5j, but these are orthonormal, so this will be just one only. So this will give me summation j from 1 to infinity aj e to the power of minus lambda js e to the power of minus lambda jt phi j x. And all of this eventually is, if you see, this is nothing but summation j from 1 to infinity aj e to the power of minus lambda j uh, S plus T phi j x. But this is nothing but, if you see, this is nothing but definition of T of T plus S at Gx. So what this implies? So that we have Ts Pt equal to T of S plus T for all S and T to be greater than equal to 0. So we have this next property as well. So we have this I would say this the semigroup property is there. Finally, we need to see one more last thing, that this so this till now this will prove that is the form a semigroup of operators, but to get the C naught semigroup of operators, we finally have to put the last property that that T of small t of G has to converge to G in L2 as T tends to 0. So thus it follows that the family of operators Pt t greater than equal to 0 forms a semigroup of operators. So finally, you have to see the continuity thing. So finally, we characterize the continuity of T, not that, for all G in L2 omega L2 R. NH positive, we have so TH G minus G L2 Rn. Okay, so this will be nothing but I just expand TH, just whole summation k from 1 to infinity, and product of G with phi k L2 Rn, and then we have this E minus lambda kt phi k, and then we have minus G whole square L2 omega. So this is definitely THG, but we also know that G has again an expansion. So writing the G in the expansion as well, summation k 1 to infinity G phi k into Rn E minus lambda kt phi k, and this is nothing but minus summation k 1 to infinity G with phi k into Rn whole square. Sorry, it's L2 Rn only. Ultimately, we have defined G on omega only, so it's omega is, sorry, it has to be omega. Maybe we can prove this for Rn, but since we are taking G from L to omega, so let's restrict to omega only. So since this now all this can be written as summation k 1 to infinity G with 5k L to omega and then E minus lambda kt. Oh, it has to be H only, so it's sorry, it has to be H lambda kh, and this is again lambda kh minus 1 5k L to omega whole square. So, but we know that these 5k are an orthonormal sequence. So this whole square can be actually written as summation k1 to infinity mod g 5k L to omega and this whole square e minus lambda kh minus 1 whole square. So this follows from uh, orthogonality or orthonormality of the eigenfunctions ik. So once we have this thing, because we have computed the difference of THG with G. So, but this basically this implies that as h tends to 0, have here is since this series is convergent, so I can break the series in two terms. So one term is the tail. So this is first of all this has to be convergent. So there's no doubt about that. So now since this is a convergent series, what we basically can show here is that this whole convergent series can be written as two sums. One is the tail and another finite term. And for those fine, the tail I can make as small as I want, and the remaining finite terms I can, if we take h tends to 0, that will goes to 0. So but basically with that divide and conquer analysis, but we can eventually we can conclude that it follows for each g in L to omega, we have the strong convergence, that is TH G converges to G in L to omega as H tends to 0 plus. we have this tt greater than 0. This forms a C naught semigroup of operators. As we can see with this, we have this basically the solutions are forming a C naught semigroup of operators, and this is something motivates us to basically study about these C naught semigroup operators, and that's why I thought that it's very crucial to put this example so that you have an idea, and then why this is all motivated and why we're solving this in manner. So yeah, it's some sort of somehow motivate from the solutions only. Okay. So next we have a question which is again based on the unbounded operators. So consider another question. So I'm taking to be L1, let is L1 space. So we have E star, or the dual of E will be nothing but the L infinity, and consider the operator A from dA subset E to E defined by A of U is nothing but NUN, and domain is defined to be as, in a way, all the U in UN which belongs to L1 such that NUN is in L1. So the part is check that A is densely defined and closed. So to show that this is densely defined, first we name that clearly C naught not so small C naught is a subset of dA, and it is C naught not not. This is eventually all those sequence in basically in L1 such that UN is 0 for all n greater than K for some K. So eventually which are eventually 0 set of sequences. Also, we know that this C naught not is actually dense in L1 is L1. This implies D of A closure is nothing but L1 only. So this implies dA is densely defined. So this is densely defined. Next we have to check is it closed. So how do we check an unbounded? So this is an example of unbounded operator. We have to check this is actually uh, closed. So how do you check an unbounded operator to be closed? We have to see its graph to be closed. So a graph of A is nothing but set of so if I try to define the graph. So graph is nothing but all those U and AU such that U belongs to my PA. Right. So this is this, and this is a actually nothing but a subset of L1 cross L1. So we need to show graph of A is closed. So if I take a U J be a sequence in DA such that UJ converges to U in UJ converges to U in L1, which is nothing but E only, and AUJ converges to some F in again in L1, which is E only. So what this basically implies, since UJ converges to U in L1, this implies summation N1 to infinity mod UNJ minus UN. This whole thing, this whole sum actually goes to 0 as n tends to infinity. Once that is there, what we have there, we have basically, sorry, at j tends to infinity. So basically, UNJ minus UN, this is less than whole summation, and that holds for all n. So and this thing as goes to 0 as j tends to infinity. So what this basically implies, this implies UNJ goes to UN as j tends to infinity, and that holds for all n in n. Similarly, with the same thing, we can prove that similarly we have a u with au aujn, so au auj whole n. This converges to fn as j tends to infinity. This had for all coordinates. But this basically what is AUN? AUJN is nothing but this is a just as you see, this is nothing but defined as just taking and you have to multiply there. So this is N U J N. This converts to Fn as J tends to infinity for all n to n, and note that n is fixed here. But we also know that U N J converges to UN and N U J converges to Fn. So in fact, we have N U N J dot has to converge to N U N, assuming since we have N to be fixed, thus we have from uniqueness of limit Fn has to be equal to NUN for all n in n, and once that is there, this is what this basically implies, that U is nothing but lies in the D only, because this basically implies that NUN is in L1 So once that is in L1, so that is the definition of physics. That is, we want to be the definition of dA. And once that is there, this actually implies that U belongs to dA. And what this will imply, this implies A is closed. So this is important as well. Determine dA star and A star. So how do I define dA star? dA star is nothing but is defined as all those functional in P star, so in the codomain, such that there exists P positive such that f of A U whole mod has to be less than equal to C times the norm of U in L1, which is E only, and it holds for every U in dA. Now, so what is E star here? E star is here is nothing but L infinity only. And this is L infinity only. So we know the whole the dual functions are nothing but the L infinity functions only. So whatever we'll claim will be, we will prove that dA star is nothing but all those V in Vn which are in L infinity, is that n times Pn will actually lie in L infinity as well. So this is our claim. So we would like to prove this that dA star has to be equal to nothing V all those V in L infinity, so that n Vn is in again L infinity, this new sequence. So if I define this to be S, all those V in Vn which belongs to L infinity, just nvn is in again L infinity. Then if we take then for U in dA, we consider V of the duality pairing of V with AU. So this is nothing but summation n1 to infinity Vn AUN, and this actually can be written as, since you know what is AUN. AUN is nothing but A is not n times UN, and as we know that n times Vn is again L infinity, so this actually can be bounded above by this actually modulus, everything will be in modulus. So this all can be bounded above by the L infinity norm of this summation n1 to infinity UN. This is nothing but the NVN L infinity norm of this, and then the L1 norm of this, so little L1 norm. And this holds for all U in this. What this implies? This implies V actually lies in dA star. So next we try to prove the other side inequality. So this actually proves that S will be a subset of dA star. And once that is there, next we have something. Let V from dA star. And then what we basically have, we have V will be in L infinity first of all, and whatever else it will hold, it will have that if the duality product of V with V with AUN AU has to be less than or equal to some constants times the L1 norm of U, and that holds for all U in dA. Right, and what is this? This is nothing but summation K1 to infinity PK AU K whole summation less than or equal to C times UL1, and that holds for all U in dA. What this basically implies? This implies if we put the definition of AUK, this is nothing but VK KUK less than or equal to C times UL1 for all U in dA. And what this further implies, if I take summation K1 to infinity KVK times UK less than or equal to C times norm UL1, and then this holds for all U in dA. So this is the relation which we have done in basic function analysis course. So this holds for all U, and this U in dA, and dA actually contains C naught naught, which is dense in L1. So then this holds for all L1. So this can be seen as a linear functional. And with this a linear functional, so this actually will lie in the dual space of L1, which is nothing but L infinity only. And since this is in L infinity, basically this comes from the duality norm. So I can divide by norm of UL1 and take the supremum. And this will actually nothing but this implies that the KVK, this L infinity has to be less than or equal to some C time, less than by the norm C only, by the duality norm. And once this is there, this will prove what this proves. This proves that that V, which lies in dA star, will actually lies in the S at S only, and this actually implies dA star is nothing but equal to S only. So this will prove that dA star is nothing but given by this form only. Moreover, with the duality product notion, we can also prove that this A star is nothing but will be given by is nothing but A star of V is nothing by N of V, and by the duality product, which is the definition of A star, we have this equality. So once we have this, moving on, we will see one more example of this duality product. But before that, let me mention one more thing, that this dA star is actually one can check that dA star is closure is nothing but equal to C naught, and but dA star uh, actually star closure which is not equal to E star. E star is something which is L infinity. So it is a case where we don't have the dA star closure to be whole equal to the E star. So it's one of the examples which shows that, but you can see by checking, and it's a good exercise to see uh, this, but not so very hard. So finally, we have one more question based on the C-note semigroup theory. So the question number 3 is the space C of minus infinity to infinity, and let NTU to be given as 1 upon square root of 2 pi t e raised to the power of minus u squared whole divided by 2t, and this I'm taking for all my u in minus infinity to infinity and for all t positive. And then define Ct on all continuous functions from minus infinity to infinity by Tdx as minus infinity to infinity and t of s minus u x u for t positive and xs for t equal to 0. So show that this family is a C-naught semigroup of operator. This C-naught semigroup of operators. So how do we show this? To show this, first of all, by definition, uh, T0 is nothing but identity only. T0 is identity only. And there's one more thing. This is a Gaussian distribution. So this will actually have a integration to be equal to 1 only. This is something which we are taking. But again, this is like very well known. First, we do one thing first, that each it is continuous. So this will help in the last assertion, as I consider the TTX norm. So norm is, since I'm considering A to be the sup norm here, which is nothing but the so let me write it in just Tt x s. This is minus infinity to infinity of nt s minus u xu du, and if we consider the modulus is less than minus infinity to infinity, so nt s minus u, so n is a non-negative function, so the mod of n is same as the n mod of xu du. This is all less than equal to the L infinity norm of x, and this is minus infinity to infinity nt of s minus u du. But this integration is 1 only, so this is actually the L infinity norm of x. What this basically implies, this implies the ttx of L infinity norm has to be less than equal to the L infinity norm of x with infinity. This actually proves the continuity of these TT operators. So they are actually bounded operators. And next, we have to check this semigroup property. Actually, this semigroup property is actually a consequence of this follows from the follows from the following property of Gaussian distribution. So what is that property? The property is this thing. So we can prove this with the help of the Fubini theorem. 2 pi t plus t dash is e raised power of minus u square 2 of t plus t dash. This is nothing but 1 upon root 2 pi t, 1 upon 2 pi t dash minus infinity to infinity minus u minus v whole square whole divided by 2t. It is power of minus v square. It's like e raised power of minus v square 2t dash. So this is by completing the square and one. And here apply Fubini theorem. We were able to prove the semi group property. Finally, we have to prove the continuity property. Basically, the strong continuity property. So if we just consider, if we can prove something more, so I will try to prove something more general, and we can take t naught to be 0 here. So ttx minus tt naught xs, which is nothing but minus infinity to infinity, nt of s minus u xu minus nt naught of s minus u xu du. So what we do, we will use a change of variable here, and the change of variable is nothing but I take s minus u by root t equal to z only. And what this will imply? This will imply dtx at s minus dt naught x at s is given by minus infinity to infinity n1z x at minus s root tz. So you can check like this after change by this change of variable we have this thing x of s minus root t naught z tz, and it's all times x's. So once we have this, I can break this integral into two terms. So using the uniform continuity of x's on minus infinity to infinity, such that for epsilon positive there exists delta, which of course depend on epsilon positive. We have x of s1 minus x of s2 to be less than epsilon whenever s1 minus s2 is less than or equal to delta. So we split the integral. So dtx s minus dt naught x of s to less than equal to integration of root tz minus root t naught z is equal to delta n1z mod of x of s minus root tz minus x of s minus root t naught z dz. And then further the integral this is value is greater than delta n1z x of s minus root tz minus x of s minus root t naught z dz. And we can use the uniform quantity here in the first integral. So integration of this n1z dz, and we can take the integration on the all of r as well, plus 2 rn 2 of sorry r only, and 2 of I can take the uniform bound of x here since uniform quantity it will be bounded, and the integration of root tz minus root t naught z whole mod is greater than delta n1z dz. Now, but we know that the integral converges since the integral minus infinity to infinity n1z dz converges. We have this thing integration mod of root tz minus root of t naught z greater than delta n1z dz. This converges to 0 as t converges to t naught. Once that is there, we have this. This basically gives the second term also goes to 0, and when that is there, this will imply that both terms will go to 0, and this actually implies that dt of x converges to Tt naught of x. In particular, holds for T not equal to 0 as well. And once that is there, this proves Tt is a T naught semigroup of operators. With this, we end up the session today. Thank you.